This is the second section of chapter 5, dynamics, and this section is on Newton's law of gravitation. Now, Newton's law of gravitation is concerned with the forces of attraction between two bodies and the link between the force of attraction and these bodies and their distance and their masses. Quite often these are things to do with like the Earth and something orbiting the Earth, or maybe like the moon. So for example, the reason why the moon doesn't fly off into space, because the Earth is like applying, or there's some sort of attraction that's keeping the moon within its orbit. The same reason that the Earth orbits the sun, it doesn't just fly off into space, because there's this force of attraction that's stopping the Earth from flying off into space. And I suppose sort of logic would tell you the further away something is from like the sun, for example, the smaller that force of attraction. And it all depends on the masses as well, because the mass of the sun is huge compared to the Earth. So the force of attraction extends far out into the solar system to sort of planets like Pluto and things like that. Anyway, what we need to know is the distance between the center of these two masses, which I'll call D. We also want to know the mass of these objects, and I'll call the mass of this one M1 and the mass of M2, this one M2. And the force of attraction is going to be this force here. Okay, so basically this arrow represents the force that this smaller object, they don't have to be different sizes, is offering or pulling towards from this larger one. So imagine this is the moon. So there'd be a force of attraction from the moon on the Earth. There's also an equal and opposite force of attraction of the Earth that's like pulling the moon towards it. So these forces are equal and opposite, which means the moon stays in orbit, it doesn't move any further away, it doesn't get any closer. When these forces become unbalanced, then something will sort of fly towards the Earth or fly away. Now, this is the bit you've been waiting for. Here's the formula here. This force of attraction F is equal to G, which is what we call a constant of gravitation, times by the two masses divided by this distance squared. Now, from what we know about mass and weight, if this was the Earth and I had a particle resting on the surface of the Earth, and this particle's mass is m, then we know that there's a force directed towards the center of the Earth, its weight mg. Now, let me just put on, I'm now just talking about the Earth here. So if this was the Earth and we took the radius of the Earth here and called it big R, and the mass of the Earth we just called m, then we can use this information in this formula. What's going to happen to this equation? Well, F is going to equal, we still have the constant of gravitation. Now the product of the masses, well, the particle on the surface is small m and the mass of the Earth is m, divided by the distance squared. Now if it's a particle, we ignore its size, so pretty much the distance between the center of these masses is r. Okay, so d squared now becomes r squared. Now, from what we've said before, the force of attraction between these two things is equal and opposite. The force that the particle has, or the Earth has on the particle, is mg. So that's like our F now. So the same is going to be the other way. And so we can replace this F with mg. So now we have mg is equal to g m big M over r squared. we can cancel out the m's. Then we will times both sides by r squared and divide both sides by m, and we will get g r squared over m. And this is another useful formula, particularly useful for when you want to eliminate g, or you don't know g, this constant of gravitation, in your working. Now you can use your calculator to find g, this constant of gravitation. So these instructions are for the Casio ClassWiz DSFX 991EX, and to do it you need to press Shift followed by 7, and you'll see it says constant, or CONST. That will bring up a menu. We want to press 1 because this is a universal constant, and then from 1 we want to press 7, and then you'll get a capital letter come up on your screen, 7, like that, and you press equals, and you'll get the value of g to a certain number of decimal places, 5 decimal places, 6.67384 times 10 to the power of negative 11. Now I don't know whether this is an exact value or whether this is sort of just rounded, or the first 5 decimal places, and that's enough for working. But yes, you can use your calculator to find this constant of gravitation. Example 8. Two particles of masses 0.5 kg and 2.5 kg are 4 centimeters apart. Calculate the magnitude of the gravitational forces between them. Right, so here's a diagram representing what's going on. The 4 centimeters, we need to change the SI unit, so we change it to meters, 0.04 meters, and this will be our distance. So because they're particles, we ignore their size, so this measurement basically is going to be the distance to the center of these two masses. Normally, quite often they're spheres, but they can be other things as well. So we'll start by writing down our formula. This gravitational force F is equal to G m1 m2 over d squared. So we'll have F is equal to, now for G, the this constant, we can actually get this from our calculators. Maybe it might be a good time now to show how we can get this gravitational constant. So if you do Shift and 7, so Shift and 7, this is for the 991EX, so Shift followed by 7, you'll notice it says CONST, constant, and then you can bring up all sorts of constants, and this is a universal constant, so we're going to press 1, and then you'll see G is number 7. So if you press 7, it will come up with a capital letter G, press equals, and I will see that I get G is equal to 6.67384 times 10 to the power of negative 11. So you don't need to memorize it, it's there on the calculator. So that can go in my calculation, 6.67384 times 10 to the power minus 11 times by my mass 1, 2.5, times by my mass 2, 0.5, divided by my distance squared, which is going to be 0.04 squared, and then we just stick on a calculator and see what we get. Right, so I get 5.2139375 times 10 to the negative 8. So 3 significant figures will just be 5.21 times 10 to the power negative 8, and that's going to be newtons because it's a force. So there is a force, a gravitational force between these two objects, but it's very, very, very small. Example 9. Above the Earth's surface, the magnitude of the force on a particle due to the Earth's gravitational force is inversely proportional to the square of the distance of the particle from the centre of the Earth. The acceleration due to gravity on the Earth's surface, on the surface of the Earth is g, and the Earth can be modelled as a sphere of radius r. A particle P of mass m has a distance x minus r, where x is greater than or equal to r, above the Earth's surface. So before I go to part A, lots of information here. This force is inversely proportional to the square of the distance of the particle from the centre of the Earth. Acceleration due to gravity is g. The Earth can be modelled as a sphere with radius r. We've got this particle on the surface that has mass m and has a distance x minus r above the surface of the Earth. So before I do any work, I'm just going to draw a little diagram so I can see what's going on. Okay, so here's my diagram. Now, this bit here where it says x can be greater than or equal to r basically means that the particle can be anywhere above the Earth and actually right down onto the surface of the Earth. So it can be any distance right down to the surface of the Earth, and that would be the case where x is equal to r. So what we're going to do for part A is use that piece of information. So we're going to be looking at the particle on the Earth's surface. Now, the reason we're going to do that is because we know that when it's on the Earth's surface, the gravitational force is going to be equal to mg. It's mass times the where is it, g? Yeah, the gravity of the Earth. And then we can use that to set an equation and then get to this expression here. So yeah, on the Earth's surface, we would have a force of mg going down. And we're also told that the force on the particle due to the Earth's gravitational force, so that would be a force that looks like this. Okay, we're told that that force there will go downwards is inversely proportional, so k over something, so we'll put F is equal to k over the square of the distance between the particle and the centre of the Earth. So the square of something, and the distance between the particle and the centre of the Earth here is x, so k over x squared. But because this particle we're considering when it's on the Earth's surface, this will be r squared. Now we can make these two forces equal to each other, so mg, I could have had here F equals mg, or mg equals F. Mg is equal to k over r squared. Then I can rearrange this to work out what my constant k is, and that's going to be r squared mg. So now we're going to consider the particle at a distance of x from the Earth's centre. So this formula here, or expression now, becomes F equals k over x squared. So now we're looking at the general case. We just used its position on the Earth's surface to help us to find k. And then from here, we can say that gravitational force F is equal to k, well that's r squared mg over x squared. So if we know the radius of the Earth, if we know its distance from the Earth's centre, and the mass of the particle and the gravity due to acceleration, we can work out the gravitational force on the particle. Right, let's move on to part B. And it says this. I think we're going to need a bit more space for part B, so I might get rid of this work in a moment. A spacecraft F is fired vertically upwards from the surface of the Earth. When it is at a height 2r above the surface of the Earth, it's at a speed half root gr. Assuming that air resistance can be ignored and the rocket's engine can be turned off immediately after the rocket is fired, part B, find in terms of g and r the speed at which S was fired. So first thing I'm going to do is get rid of this working here and also update my diagram so I can use it for part B. So here's my updated diagram. Here's the spaceship here, distance of 2r from the surface of the Earth. The Earth still has a radius of r. The gravitational force on the spacecraft from the Earth is F, and that is what we've worked out in part A. So we're going to be using that in a moment. And its velocity or speed, which is half root gr, directed away from the Earth. So we're going to take going away from the Earth towards the spacecraft as our positive direction. So we start with F equals ma. And as I said, we are taking, in my diagram, upwards as positive. So our force is going to be negative F is equal to the mass. And actually we've worked out F, haven't we? This is our gravitational force, so let's stick that in. Sorry, not minus F, but it will be minus mg r squared over x squared is equal to ma. We can cancel out our m's like this. Let's just move the minus down to the middle like this. And then since we want to find the speed at which it was fired, we want to replace a with v dv dx, because then we've got velocity and we've got distance, which is what we've got here, and then we can separate out the variables. So we'll do that now. So what I've got now is minus gr squared over x squared is equal to v dv dx. Then separating out my variables, so I'll keep the constants here on this side of the integral sign. That will leave me with 1 over x squared. I'll bring over the dx. Then on the other side, I'm just left with an integral of v with respect to v. So integrating first of all the left hand side, the 1 over x squared, that's x to the minus 2, that will be x to the minus 1 over minus 1, in other words minus 1 over x. So that minus is going to cancel out with this minus here, just leaving me with g r squared times by 1 over x is equal to half v squared plus a constant of integration. So I now want to work out that constant of integration. We look through the question. I'm looking for a distance and a velocity, and that piece of information is here. When it is at a height of 2r above the surface of the Earth, its speed is half root gr. So x is going to be the distance of the spacecraft from the centre of the Earth, 2r plus r, that's going to be 3r. And our velocity v is going to be half root gr. So we'll substitute those in and we'll end up with gr squared 1 over x now becomes 1 over 3r equal to half v squared, so that's half root gr squared plus c. Lots to simplify here. On the left hand side we'll have gr over 3, I think that's right because the r's will cancel out, is equal to, so if I square this side that will become a quarter, so then a quarter times a half is 1/8, and then I'm going to square the square root here, so that will just become gr, so I could write that as gr over 8, gr over 8. I've got plus c, so now I can work out what my c is. So that gives me c is equal to 5 over 24 gr. So my full expression now is going to be this with my value of c, so it's going to be let's write it like this, gr squared over x is equal to v squared over 2 plus c, and I'll write that as 5 gr over 24. So going back to the question, I want to find the speed at which it was fired. Now when it was fired, it was on the Earth's surface, which means that its distance from the centre of the Earth, x, was just r. So now we replace x with r because it's on the Earth's surface. We want to find the speed, we want to find v. So we replace x here with r. So we'll have gr squared over r. Well, that will just become gr. So we'll just simplify that there. Gr is equal to v squared over 2 minus 5 over 24 gr. So now if I times both sides by 2, then this 2 goes here, so that can just become v squared. If I times the 5 over 24 by 2, that just becomes 5 over 12. And then this becomes 2 here. I can rearrange it and say that v squared is equal to, that will be 2 gr plus, will it be plus? No, it should be, that shouldn't be a minus there. Let me just check my working again. So yeah, I've put a minus here. I'm not sure why. That should be a plus. Sorry about that. That should be a plus, which means as it moves to the other side, yeah, that's a plus because that's a plus. I wrote a minus by mistake. So that will become minus 5 over 12 gr. Now I can do those together. If I do 2 minus 5 over 12, I get 19 over 12. So let me just replace all of this with 19 over 12 gr. Okay, 19 over 12 gr. I'm doing this because I haven't got a lot of space. So that means that v is going to be the square root of that. So it's the square root of 19 over 12 gr. So there we have the speed of this spacecraft in terms of g and r. So you should now be able to do exercise 5b on pages 183 to 184 of the textbook.